Hi, I'm Einat, and I'm going to talk about the measurement-induced phase transition in Clifford circuits with measurements. Okay, so I'll start with motivation. So some of the challenges quantum computers are facing right now are related to them being open quantum systems. It means they interact with environment and exchange energy and information. It introduces a lot of noise and keeps them out of equilibrium. So one way to address such systems is to model them as closed quantum systems with non-unitary dynamics. And in such system, one can observe the measurement-induced phase transition. So there are like mutual benefits of quantum computers and measurement-induced phase transition. The first and obvious one is that quantum computers are very clean experimental systems, so you can observe the measurement-induced phase transition using simulations. And the other way, which is more interesting, I think, is that you can get insights on quantum computers and the challenges they're facing by understanding the measurement-induced phase transition and the mechanism behind it. Okay, so this is the outline of the talk. I'll start by introducing the measurement-induced phase transition. Then I'll show the minimal cut, which is like some kind of analytical argument to explain the measurement-induced phase transition. And then I'll talk about the measurement-induced phase transition in Clifford circuits. Okay, so consider an initial state of, which is a product state of spins. Then when you apply a unitary time evolution, it scrambles the qubit between them and generates entanglement. And when you measure some of the qubits, they get like some of the information is lost, the information that is related to these qubits, and this lowers the entanglement. So this competition between the unitary time evolution and the measurement results in a phase transition. So this is the way to describe it. Any unitary time evolution can be approximated by a brickwork of local gates. And then you can define a measurement density after each, like on the links between the gates. And like place the measurements. And then you can approximate the circuit to a classical network where the gates become nodes and the measurements are like decimation of bonds. And then when you increase P and add more and more measurements, you get a percolation transition where the classical network breaks into small pieces. So by a numerical simulation, it turns out that this mapping to percolation is not exact in all cases, and like only in certain limit. And in the general case, the quantum transition of the entanglement is lower, and it also has a different universality. And an interesting question is what's the universality of this transition? Why it's different? Okay, so to explain the idea behind the measurement-induced phase transition, now we'll talk about the minimal cut. So first I'll explain what a minimal cut. A cut is some way to separate the circuit or the graph into two parts. And the minimal cut would be the cut with the least number of bonds cut. So like here, cut 1 is a minimal. And it was proved that you can use the minimal cut to bound the entanglement entropy, which is the measure of the quantum information shared between two subsystems. So when drawing a cut that starts between the two subsystems, the minimal cut is a bound on the entanglement entropy, and for high random circuits, it's a tight bound. Okay, so when adding measurements, the measurement is like a free pass for the cut, and now we want to understand if the minimal cut when adding these measurements is still a tight bound. So adding the measurements is like a picture of percolation. And for the explanation, I will use like such a abstract drawing where the gray area is entangled, and the white area is where there are a lot of measurements. So when P is smaller than PC here, then most of the circuit is still connected, is still entangled, and there are some small areas of measurements. So if the system size is increased, the cut has to go through a more entangled area, and the entanglement grows. So this is the entangling phase, and in this phase, the entangling grows like the system size. And this is called the volume law. And when P is larger than PC, then most of the circuit is measured, and the cut would have to go only through small connected or entangled pieces. So the entanglement would be constant with the system size. So this is how you get like this phase diagram. So this was like the minimal cut bound, but what actually happens when doing numerical calculations? Then you can see it was shown like in the cited paper. That for infinite local Hilbert space, the transitions are the same, like the minimal cut picture is exact. But when going to finite local Hilbert space, the transition goes down, the transition of the entanglement. You can see it in this picture where the circuit seems to be connected, and the cut seems to have to go through like a lot of areas, but still at the end it's blank. So the quantum information can't pass, and and also this transition has a different universality. This is the entanglement universality, and this is the percolation universality. Okay. Okay, so now I'll go to discuss the measurement-induced phase transition on Clifford circuits, and I'll start with explaining why we picked them. So I showed in the last part that for Haar random circuits, the minimal cut bound doesn't fully describe the transition. And in Clifford circuits, we still have a different universality. So we might, again, get a different universality for the entanglement transition. But also, the Clifford circuits can be, they are not non-generic, so the mean cut bound doesn't apply. So we don't know what we would get. And also, they can be simulated classically in large scale, which makes them very appealing. Okay, so now we'll discuss the nature of the measurement-induced phase transition in these circuits, and we're going to see that even though it looks like they have a different universality and we might get something interesting, still they are controlled by classical phenomena. Okay, so this is the model we picked. It has like the phase diagram of R and P, and the 4 gates: C0, swap, identity, and bell pair. And in each point in the phase diagram, you can sample different circuits. And I want you to notice that in the whole phase space, there is no percolation transition. The circuits are connected. Okay, so for each point in the phase space, we sample a lot of circuits and collect and compute the mutual information, which is the entanglement between two distant parts of the circuit. And it allows us to use a Binder cumulant to find the transition points. And this is how we draw this phase diagram with R and P, and it has an entangling phase and disentangling phase. And we know that there is no percolation transition. So we still want to try to get some mean cut bound, or some like something that looks like this. And we do this by using the ZX calculus, which is a diagrammatic way to describe circuits and states and quantum processes in general. And its building blocks are the ZX spiders. And it's powerful because it has the ZX rules, which allows you to simplify circuits or diagrams, as I'll show. So we take the same model and use it to draw the circuits as ZX diagrams. And then we have a simplification algorithm, which I'm not going to explain, but I'll show like the way it works. It basically takes small parts of the circuit and simplify them locally using the ZX rules. So here there is one example of part of the circuit. You use these three rules, and you see that from these connected diagrams with 5 spiders, you get something that is very disconnected and simple. So when applying the actual simplification algorithm, you see that the diagram that was sampled from the entangling phase stayed connected, but the diagram that was sampled from the disentangling phase got separated between initial time and final time. So it means that while this circuit looks connected and like the information flows from the initial time to the final time, actually there is no connection, there is no passage of information. Okay, so here again, we sample a lot of data points in the phase diagram, simplify the circuit, and calculate the probability of having a path between the initial time and final time. And from this, we get a percolation point, which is the transition point. This is an example for a specific R. And we plot these transition points on the phase diagram. And you can see that the red points, are matching very closely the mutual information line. So the mutual information can be described by percolation on the simplified circuits. Meaning the measurement-induced phase transition on Clifford circuits is a classical percolation transition in disguise. Okay, so now I'll sum up. The competition between unitary time evolution and measurement results in a dynamic phase transition. This phase transition can be bounded by the minimal cut picture, which is exact in the infinite local Hilbert space and makes the transition map to percolation. But in finite local Hilbert space, the entanglement transition PQ splits from percolation transition. Clifford circuits they have a different, seem to have different universality, so they may be a way to see a new phenomena. But our ZX simplification technique indicates that the transition is just a simple percolation in disguise.
So thanks for the talk. So if eventually these Clifford circuits are percolation, so how comes that the critical exponents are different?
We actually haven't looked into that yet, but wait. Okay, no, never mind. Okay. Here you see it's not like this simplified circuit and like the probability of having a path between the initial time and the final time is not exactly the classical percolation. So it might be related to that. Maybe we have to look more closely into these circuits. They are not Erdos-Renyi circuits. So this might be the reason.
Maybe I can just comment that the idea is that when they look at the universality, they assume the structure of the circuit is this brickwork kind of structure. What she meant, what she said basically is that the operations she's performing are not local, and therefore nothing ensures that